All right, let's get started. Welcome, everyone. Today, we're going to talk about representation learning in reinforcement learning. But first, a couple of announcements. This is the before last lecture. Next week is the last lecture. Next week, we have Aaron Vandenoord visit from DeepMind. So that's next week's lecture. And then, aside from lecture, what's still doing the class is final project. And so there'll be a sign-up going out for final project presentations. And there will be also a due date coming out sometime soon for when your final project reports are due. Any questions about anything logistically?
When should we get the feedback from the final project milestone updates?
So if you submitted it by the deadline, you should have already gotten feedback. If you did not, send it to us again, because somehow we must have missed it. If you submitted it after the deadline, hopefully soon. All right, so I want to start out with a few acknowledgements. What we're going to cover today could really be like 10 weeks of lecture, and there's a lot of materials. And there are many people who have contributed to these materials. So Abhishek Gupta, Max Jederberg, David Ha, Martin Riedmüller, Janger Hafner, Marvin Zhang, Carol Greger, Blase Rzinski, Irina Higgins, Pieter Sermone, Ashvin Nair, Vichy Pong, Rico Chinchowski, Deepak Pathak, Pulkit Agarwal, Colleen Devon, Chelsea Finn, Amy Jang, Alessandra Akil, and Greg Kahn all send slides, illustrations, share their insights in terms of what we're going to cover today. So big thank you to them, and let's get started. So everything we've seen so far has been about, in some sense, unsupervised learning with supervised learning in mind. The idea that labels are hard to get, so it'd be nice to have a representation, so now you need a small number of labels and you can use your representation that you learn from unlabeled data. But there's another problem out there, reinforcement learning, which is kind of a bigger problem in AI in some sense. It's not just about a one-time decision about what's in some input, but trying to make decisions over time. And so in reinforcement learning, an agent will look at the environment, based on what's in the environment, make a decision, what action to take, and this process will repeat over and over and over. And over time, the agent might collect reward or might not collect reward, depending on how well it performs. For example, for a self-driving car, maybe positive reward for getting to destination, negative reward for accident. And this has a lot of new challenges in terms of how easy it is to build, or how hard it really becomes to build an agent that can do this well. One big challenge is credit assignment. An agent doing reinforcement learning might get a reward once after a half hour of interacting with the world and might not know which actions were relevant to getting this reward and which ones were just wasted time or even detrimental. Stability, because if you're controlling a system, you could destabilizing it. And if you destabilize it, then you might get very negative reward or the system might just die on you. And then there's a challenge of exploration. And so with these challenges in mind, we're going to start thinking about how we can maybe bring in unsupervised learning to make reinforcement learning work better. Let's first take a look at some successes already out there in reinforcement learning. So one of the big successes with deep neural networks and reinforcement learning is learning to play Atari games. And the first breakthrough there was in 2013, Vlad Ni and collaborators at DeepMind. And from there, many more breakthroughs have happened showing that it's possible for a deep neural network to learn to play any of the Atari games at pretty reasonable performance. Then, a little later, was the breakthrough in playing Go. A lot of people thought it would take a long time before there would be good performance on Go, but it turned out that it was possible with reinforcement learning to train an agent to play Go really well, in fact, better than the best human players. OpenAI looked at playing the game of Dota 2, a very popular video game. Originally, they simplified it to one-on-one. That was in 2017. Beat the best players one-on-one. Then in 2018 and 19, they showed it's possible to also reinforcement learn to play a team of 5 agents that can beat some of the best human teams out there. And then in robotics, there's been quite a bit of success. A lot of this specific work happened at Berkeley. What we're watching here is some reinforcement learning in action. So the robot is initially not really capable of running, and it just falls over, but through repeated trial and error, it figures out what it takes to run as far as possible to the right for us. and actually can stably run after 2,000 updates to the network. And the beauty, of course, with all of these reinforcement learning results is that the systems learn from their own trial and error. You don't have to constantly tell them what to do. The other beauty is that you can use the same piece of code to learn to run with 2 legs, or then if you have a 4-legged robot, you can just run the same code and it can learn to control the 4-legged robot. Or you could put it in front of the Atari games and it'll learn to play the Atari games. In each of those cases, though, one of the challenges is it can take a little bit of time before it actually acquires those skills. Because for each iteration here, an iteration is one update to the network, but actually a bunch of experience has to be gathered before there's enough signal there to do a good update to the network that improves performance. And here it is learning to get up. Slightly harder task in some sense. The higher it can get the head, the better, and it learns that standing is better than being on the ground. And in fact, by now it's possible to train these agents to have a very wide range of physical skills. And it's also possible to train real robots to do these things. So this is Bret, the Berkeley robot for the elimination of tedious tasks. This robot lives on the 7th floor of Sutarja Dai Hall. And here is practicing to put the block into the matching opening. What's the catch? Despite all these successes, there is still a big catch, and that's the data inefficiency. For pretty much anything you want to get to work with RL, you have to wait a very long time before you finally get that good performance that you're after. And sometimes the problem might be too hard, and you don't even have the patience to wait that long, and the success hasn't happened yet. And so the question is, how can we bring in other signal to learn more quickly, aside from this sparse reward that is really holding us back because it doesn't give us much signal? So there's a few different angles in which representation learning can help in reinforcement learning, and we'll go through all 4 of these in today's lecture. So one is auxiliary losses. At a high level, it might be kind of clear what might be happening here is that you give your network multiple heads, and by giving it additional heads, the core of the network might learn more quickly, and then you might also learn to behave well more quickly than if you didn't have these additional heads with auxiliary losses. State representation is a big one. If you get in pixel values, usually the pixel values are very high dimensional. Maybe you have 1 million pixels, but really it's just 3 objects. And if it's 3 objects, that's in some sense 3 times 6 degrees of freedom. That is 18 numbers summarize the pose of these objects, whereas it would be 1 million pixels to see them. And so going from this high dimensional representation, something more amenable to learning, something lower dimensional can be very helpful. Another big challenge is exploration. If your agent hasn't done things before, it needs to try things that are interesting to try. How would it know what is interesting to try and is promising versus would just be probably a waste of time to try that? And then another thing is that sometimes you want to be even more unsupervised. So you might say, well, I'm happy to give rewards and train my agent. You might also say, well, I don't even want to give rewards. I want my agent to just on its own, completely unsupervised, try to train itself and acquire a wide range of skills that can later be reused maybe to do new things. So that would be unsupervised skill discovery. Okay, let's start with auxiliary losses. This was one of the kind of first very successful results in representation learning for reinforcement learning. It's from Max Jederberg and collaborators at DeepMind, and it's often referred to as Unreal. For unsupervised reinforcement learning with auxiliary tasks. So what happens in Unreal? The problem is that, let's say in these Atari games, especially Montezuma's Revenge, the reward is very, very sparse. And so if all you do is die when trying to play this game, you get only signal that everything you do is bad. And so then you don't learn much of a representation of how the world works. But in principle, you should be able to learn other things about the world than whether you get reward or not. And so the question is, how do we introduce that into the agent's architecture? The result, ultimately, for the Unreal agent is a 10x improvement in data efficiency over the previous state-of-the-art at the time, A3C, on the 3D environments that are called DeepMind Lab. and a 60% improvement in the final scores over A3C. A3C is a standard policy gradient algorithm. I know we haven't really covered reinforcement learning algorithms here, but it's just a policy gradient algorithm that DeepMind likes to use. Okay, so what's the architecture at a high level? We have an agent that uses the standard A3C architecture, which is shown over here. There's an observation, goes into the agent. Then there's an LSTM here. Because it's in a maze, it's good to keep track of where you've been in the past rather than just paying attention to the current observation. So a recurrent structure is good. So there's an LSTM structure here, outcome, value, and policy. So that's the standard A3C architecture. What's going to be added on is 3 components. One called pixel control. We'll say more about that in a moment. Another one called skewed sampling, and another one called value function replay. And we'll dive into all 3 of them in the next couple of slides. The key here is that by adding auxiliary tasks to the same network, giving it additional heads, it'll start learning something about the world that just from the rewards it would not have learned, or not yet. Yes?
A3C is a policy gradient approach, but this says that Unreal can go on top of like DDPG and DQN, which are Q-learning.
Yeah, so it doesn't really matter which RL algorithm you run for this idea to work, because the idea is centered around the architecture of the neural network, and the neural network getting auxiliary losses rather than what you use for RL. What is kind of interesting is that here you can use it on top of a policy gradient method, which is on policy, whereas very often when people try to do things, it might end up requiring off policy algorithms, and that's not needed here. And so DeepMind did their experiments with A3C largely because that's the algorithm that kind of they had most consistently up and running at the time, I imagine, and could most consistently get results and get good comparisons out. Whereas often Q-learning is harder to get to work, whereas policy gradient methods is more straightforward. They'll gradually increase performance over time. So the cake comes back again. Motivation remains the same. The story of the cake remains the same. The cherry is only one cherry, a very sparse signal. The foundation of the cake is much bigger. How do we get as much signal as a foundation? Is by introducing these auxiliary tasks. So how do we get them? Well, one way is to get many reward signals. How do we get many reward signals? It's through doing pixel control. So what is pixel control? The very specific incarnation here is the following. You see a current view, and you're gonna, in addition to learning your policy and your value function, you're gonna learn a Q function. This Q function is gonna assign a value to each action you could take. And you're not just gonna learn one Q function, you're gonna learn a Q function for every pixel in your image, or every averaging of pixels in a region in the image. And what you're going to do is you're going to say, okay, I get reward if I can change the value of that pixel. So for example, the Q value is here. Imagine there are 3 actions, then that would be correctly shown over here. Then this would show, if let's say bright is good, that the second action is one that has a higher probability of changing the pixel value in this particular pixel in the image the agent is seeing. This is second best, and the one in the back is third best. And so for every pixel, it gets supervision. You can imagine doing other things. You can imagine doing something where you say, instead of trying to predict which action will change the pixel value the most, you could maybe say, I'm going to predict what the pixel value is going to be at the next time. That would be a very reasonable auxiliary loss too, but it would not be tied as closely to things that are under your control. And they found that this is actually working better, that it's better to tie it to Q values and things that are related to an agent trying to achieve things rather than just doing next state or next observation prediction. You could also imagine that you would prefer to do this in feature space. That's what they call feature control. In their experiments, feature control did not work as well as pixel control. So feature control would be that somewhere in the latent space you designate a feature layer, say that's my feature layer, and I want to learn a Q function that says which action, how much will each action change the feature values? over the next few time steps. Not sure what the horizon would be for Q-learning here, but that didn't work as well as doing direct pixel level control. Yes?
Do they have gradients flowing from this feature control to the features themselves? Because for example,
that's a good question. We'd have to check the paper for that. Indeed, you could set it up both ways. You could set it up where you flow back into the features or where you stop it at the features and let something else learn the features. I think if you don't let it learn the features, then it's probably not going to help you that much with what you're trying to achieve here. Because in this case, the hope is that by having the pixel level control as an extra task, but many pixel level control tasks, that you learn representations of the environment more quickly than you would otherwise. And if you don't let yourself learn features based on it, then it kind of defeats the purpose. But I could imagine another additional feature level control on top of all of this that maybe doesn't flow back and could help at a later stage.
Pieter,
Yeah?
So if you're doing feature control, so like say the objective is to maximize the feature, right? Even if you clip it, like all it's going to do is make all the values as big as possible, right?
Yeah, so that's the tricky part with when you flow back into it. So you might not learn good features, but it'll be competing with other things you try to do with the features. So yeah, it's not clear how it would play out.
Yeah, I'm just wondering if just maximization itself might not make sense. But
Yeah, so in this case, the objective is not maximization of features or pixels, it's actually changing them as much as possible. So to see if you can change the value to something maximally different. And that's what you get rewarded for in those auxiliary cube functions.
but then you're incentivized to learn features that change very quickly, even with small changes in the pixels, right?
Are you incentivized to learn features that change more quickly? Probably, yeah.
So the action space is continuous or discrete?
DeepMind Lab, I believe the action space is discrete. I don't think you could do it otherwise because they have essentially the output here is a image again. One image for the first action, which is not a visualization of what you see, but is a visualization of the Q values for that action relative to changing pixel values at each of those spots. Same for the next one, next one, next one.
But it's not done for each pixel, right? It's done for patches or something.
I think it's done for something slightly bigger than pixels, slightly bigger, some kind of average region, because otherwise it might be too easy to change. But it is done it's done without any actual feature processing. It's done at the actual pixel values, maybe averaged. Yes.
Wait, so you grid out the input image, and then for each grid you take a separate action? Is that
So you don't take separate actions. Q-learning is off policy, right? So the beauty of Q-learning is that you can just run Q-learning on many things in parallel. And so you can just think that there is a Q value associated with how fast this region changes. There's another Q function you're learning related to how fast this changes. Another one related to this, this, and this. So for this picture here, there would be 9 Q functions that you're learning in parallel for 9 different tasks. And what does it look like to have a Q function? Essentially, one Q function is this. Another Q function is these 3 here. Another Q function is these 3 here. Not the entire function. That is the output for the current input. If you see something else, it'll of course output something else.
how do you ensure that you're doing like proper exploration in this Q function space?
Oh, that's a separate issue. Yeah, let's not get into that. We want to focus on the representation learning here.
Okay.
But you can do off policy, so in that sense, it's fine. Like the Q values are fine with any off policy. So if you want to do a lot of exploration, they will be okay with that. But A3C is an on policy algorithm, so it'll actually run on policy against the reward.
So there are multiple auxiliary tasks for unsupervised RL. What do you think is the best one? I mean, the intuition of choosing the unsupervised learning task to help with RL.
Yeah, that's a good question. What's the best one? I think it's a question for 2.5 hours from now. We have a lot to go through, and then you can maybe make up your mind on what you think is more promising.
So here, pixel control is also eyeing LSTM, right? It has some temporal relation.
Are you asking what does the Q value look like?
So I mean, it's still LSTM for...
It's the same model that's shown over here. It just has an additional output. That's the whole point. Because by giving an additional output, you're doing shared representation learning between the two of them.
It's shared network.
Yes.
Okay.
Mm-hmm. Yeah.
So the other two auxiliary tasks, the reward prediction and value function prediction, they're just supervised, right?
So let's get to those. So the reward prediction is looking at outputs from the, essentially there's feature learning happening. This the features coming here are the same as the one the A3C agent uses. They're exactly the same. And so it's an auxiliary task to predict how much reward will be accumulated over, let's say, these 3 time steps. And that also helps learning representation because maybe you get reward for grabbing an apple or something, and then if there's an apple in the frame and you're looking at it and you're moving towards it, and then it's gone, then you should predict that reward was acquired, and hopefully your representation starts picking up on the notion of trying to understand where apples are in the image. So that's the skewed sampling, what they call it, or reward prediction. And again, it's fine that this is off policy, even though A3C is on policy. These are just auxiliary losses that you can just run on the side for representation learning. And then value function replay. So what this is doing is essentially saying that you want to predict from the current state how much reward you will collect over the next maybe 4 time steps or 10 time steps, whatever horizon you use for your value function. And that's yet another way to learn about how promising the world is. And if you know how promising the world is, that probably relates to understanding things that matter. Like if you're facing a wall, that's not very promising because you can just bump into the wall, there's nothing there. But if you're facing some interesting fruits to collect, then the world looks very promising, and hopefully you learn then that's high value because there will be rewards if you happen to run into them. And then you'll understand that something related to representation of these things that you can pick up in the maze is good, and you should learn about that. So how does it look? Here is a bit of an ablation study. Unreal, the full agent, is shown in blue at the top. Just using pixel control. So forget about the reward prediction, forget about the value function replay. Does almost as well. So a lot of it must come from the pixel control objective. Doing the reward prediction plus value replay is a little bit behind that. Just reward prediction is not nearly as close, and just value replay doesn't help that much at all. So it seems like a lot of it's coming from the reward prediction and the pixel control tasks. Then here is a comparison with feature control. And there was a good question earlier, kind of, do you backpropagate into it or not? So you have to check the paper for that. What you see here is that both feature control and pixel control outperform having just A3C. And just keep in mind, when I say feature control, pixel control, it does not mean that the agent actually executes control based on those objectives. It's just that it, on the side, has an auxiliary objective that's Q-learning against pixel control or against feature control. It's not a policy that it's executing, it's just an auxiliary objective. Both of them help, with pixel control helping a little more. Then some more baselines. So you could say, well, okay, what else could we have done? Standard A3C is again shown in black. Then you could say, well, why not just input reconstruction? You have a frame, you feed into a VAE, you decode it. How much would that help? That's the green one. In the environments it tested in, it wouldn't help too much. Helps a little bit over there, not too much over here. Just input change prediction. So what that means is that the blue curve here is, instead of having a Q function around whether you're able to change a pixel based on what actions you take, you just predict whether the input will change or not in the next frame. So it's a more passive version of the Q function auxiliary loss. It also helps, but not nearly as much. And the pixel control is what helps the most. So it shows that tying the representation learning into action helps a lot in here. Yes?
Do you know if they like evaluated on like other things rather than just like the
other than the DeepMind lab environments? Yeah. I think they did a bit of an evaluation in Atari also. Here's Montezuma's Revenge, where it also helps quite a bit, it seems, compared to regular A3C, because regular A3C is actually at the bottom here, is staying at 0, and everything else is getting much higher. There's unreal in blue. Not sure. I think this is the median. I think this is the best run. Then reward prediction and value replay in purple does almost as well here. So here the pixel control might not play as big a role. It's just that gap here for the max. But then for the average, actually, it does play a, let's see, the average would be this difference, and that's a pretty big difference here. Yes?
So I'm just trying to figure out sort of, so you're talking about these auxiliary Q functions, just when you actually implement this, so is the action selection here as with Q learning, where you sort of choose the action that has the highest?
The action selection is all based on A3C. So
okay. Is that distributed Q?
A3C is a policy gradient method.
Okay.
So it's straight up policy gradient with a value function baseline. And so that's just running as normal. It's just that you give the network some extra output, and that extra output, what you do with it is, let's say you were to run Q-learning on these other tasks. In Q-learning, you don't need to control the agent to get to run it. You just need to have a sequence of data, and you can run Q-learning on it, and that's what's happening on the auxiliary outputs. It's just taking data collected under A3C, which is the on-policy the policy gradient method, and the Q-learning is just happening on the side of policy. Yes?
For the A3C plus input reconstruction, you use VAE. So you use the latent code for the VAE or the reconstructed image of VAE for your A3C?
We'd have to check the paper to be sure, but my guess would be that it's not, but that's not really the right question to ask. I mean, it's essentially looking at this architecture here that we've been looking at all along. You encode and feed this into your LSTM. So you're making a code here, and it's something about, is this a good code, a good summary of what you're seeing? And your VAE would try to decode it back into an image, and that would be an auxiliary loss, whether you have a good compression of your image into something. That would be probably the most natural way to do it.
So use a latent code, right?
What do you mean with use a latent code?
So the states for the A3C, so policy gradients.
Well, they already use a latent code right here. I mean, it's the same thing. It's just that there would be an additional loss coming out for reconstruction. Okay. Just like here, there's an additional loss coming out for Q values. It's just the same thing. Instead of Q values coming out, would be a reconstruction loss coming out.
The question was whether there is a variational inference going on.
Variational inference, not sure. Whether there's a Gaussian prior on it, who knows?
I think they just use regular auto.
Because I think it's called just reconstruction. So, yeah.
Peter, do you have any thoughts on why this PD learning objective works, kind of works better than likelihood of future prediction?
Oh, the Q-learning one?
Yeah, like in general, that seems to be.
My hunch is that it works better because it ties into what you control as an agent. So to learn to do well in an environment, you need to not just learn about the environment on how it behaves, but even more so about what you can influence in the environment. And so by looking at the Q functions, you're looking at what you control and focusing your representation learning on that. Whereas if you just do reconstruction or just do next state prediction, you're not really focused on what's under your control. And we'll actually see that come back in quite a few of the works that we'll cover later, where the notion that what you control matters more than just reconstruction seems to be pretty relevant. Yeah?
So in this case, we basically, we predicted, given any action, what the change is going to be. If we instead predict, given any action, what the future is going to be, how does that compare? So
well, that's so input change prediction, I think is what you're alluding to.
Is that by action? Is that like split by action?
I don't know if it's conditional on the action actually taken. I don't know. Otherwise, you'd have to collect multiple actions, I guess, in the same state. So probably it's based on the action you actually took. I'm going to move to the next part, because this is like 5% of what we're going to cover today. I want to get a lot of ideas across. So let's actually watch this in action. So for a lot of the things we're going to cover today, we're actually going to go a little bit faster than in previous lectures, because we could do 10 lectures on just representation learning and RL, and we only have one. But I want to make sure we always do, whenever possible, is to watch some of the videos or see some of the screenshots of where the experiments were run. Because I think that gives a bit of a feel for the complexity of the environments that were tackled with this approach. Because to be fair, it's sometimes hard to understand which method is better than which other method. The comparisons aren't always out there, but at least by looking at experiments, we can get a sense of, okay, well, this is 3D navigation. That's somewhat non-trivial compared to maybe, I don't know, moving in a grid world, a 2D grid world that's 5 by 5, right? And so this is reliably finding fruits in this world. So yeah, that's pretty impressive. Different kind of versions of this world. You can also see at the top here how often it collects reward. Initially, it wasn't very often. It's very sparse. Now it's getting reward a lot more frequently than initially. All right, so this is a summary of what this does. There is now multiple losses, the A3C loss, which is the policy gradient loss. There is the pixel control loss, which is weighted by some lambda PC. There is the value replay loss weighted by lambda VR, and there is the reward prediction loss weighted by lambda RP. For the pixel control, this was one of the question earlier, how are these pixels clustered together? So it's split into 20 by 20. The cartoons we saw were 3 by 3 to explain the method, but so the actual experiment was 20 by 20. The reward prediction, that's also interesting little piece of information there. The data that was used to train the reward predictor was sampled in a way that's not everything you've experienced equally likely to sample, but to make sure there's a balance between getting reward and not getting reward. Apparently, that's how you get more signal. Also tested on Atari, where it learns faster to some extent and gets to a higher performance than some of the Q-learning methods in 250 million frames. The difference isn't that high here in Atari compared to just running straight up A3C. This is, I think, averaged over many, many games. That's one of the evaluations DeepMind does. They will have a suite of games and averaged over all the games together, see how well you do over time relative to human performance when humans have practiced for a while already.
Is this averaged over all the games?
I think this is averaged over all the games, but then I think they run something like 20 random seeds or maybe 10 random seeds per game, and then they take the top 3 agents and show the average performance of the top 3 agents on each game, which is a little funny. It's like you take the 3 more lucky seeds. You could say that's not great. I mean, it all depends on what you're trying to do. If you want to build, let's say, the best Atari agent, then, if your method, if you run it 20 times and one of them is really good and the other 19 are not good, you can still retain that one that's really good, and that solves your problem. If you want a learning method that always learns very consistently, then you probably don't want to exclude any of your runs from your average because you're kind of hiding the fact that maybe some of them don't learn that quickly. It depends on your objective. But I think some of the recent work kind of goes in this direction too, because if you look at population-based training, there's multiple trainings happening at the same time, and the ones that are doing better are retained, combined together to ultimately, like with minimum compute, get to a good agent, as opposed to finding something that makes every individual agent go to the maximum performance.
Random seed hyperparameter search.
Yeah. And there's also a question there. I mean, top 3 out of how many can play a role, of course, and how high this graph will go. Robustness in labyrinths. So this is looking at the population of agents. So this is actually addressing some of what we were just talking about and see how the performance decays, which fraction of agents gets to a good level of performance, and which ones might not learn that well. Okay, I want to switch gears to another one, state representation. First sub-bullet, going from observation to state. So this is a very natural thing you might want. You might say, I don't want a million pixels as my input to then decide what action to take. I'd rather know the coordinates of the 5 objects that matter and take those as input and learn from that what action to take. So there's a bunch of work on this. I'm not going to go chronologically here, but I'm going to actually start from some work that is relatively recent. Perhaps the simplest way to do it, and works surprisingly well. So this is called World Models. It's by David Ha and collaborators. And here's the idea. You have an observation, pixel values. You use a VAE to compress it into some latent code Z. Then you reconstruct. And that's now your new representation of the world. You get a frame. Z is your representation. Well, a little more to it than that. You're in a world where you might not see everything at all times. You might be running around. So you want to remember some things from the past. So there will also be an RNN model that retains state from the past, and that can also try to predict the next hidden state. Okay? So what's happening here is that first you train a VAE. Once you're done training a VAE, you train a dynamics model in the latent space to predict next latent state from current latent state and current action. That's the PZT plus 1 given AT, ZT, and HT. So the latent state has two parts. Is the compression of the latest image you're seeing and the hidden state you have from the previous, from all past that you built up so far. So H lives inside the LSTM or the RNN, whereas Z comes from your VAE encoding your image, your current image. Then what you can do is you can say, oh, let's attach a policy to this. So we'll feed both encoding of the latest frame and our hidden state from all past kind of compressed together into a controller. This controller will take action. This action will affect the RNN because it'll then try to predict a next latent state based on that. It'll also affect the environment, of course, and things will repeat. And the policy they use is very simple, just a linear policy in the latent state and some offset. This is probably the simplest thing you could try to do. Once you've looked at unsupervised learning, you say, well, yeah, let's learn a latent representation. Let's learn a dynamics model over it because there will be some dynamics in the world, and let's put a policy on top of it. If you do it right, though, it can solve some problems really nicely. One example they looked at is car racing. So we're in a world here that can be randomly generated where there is a path, and that path can curve as you move along this road, and everything else is green. That's where you're not supposed to go. You're supposed to follow the road. They collected 10,000 rollouts from a random policy, trained the VAE to learn the encoding and decoding, then trained the RNN to learn the dynamics model in the latent space, and then they ran evolution, very simple method, to learn the linear controller. And they started getting pretty good scores after just 100 trials of running this. What's also really interesting here, pay attention to the cake picture again. So here's the cake. Reinforcement is supposed to be the cherry on the cake. Well, the number of parameters in the policy is 867. The number of parameters in the RNN is 400,000. The number of parameters in the VAE is over 4 million. So we indeed see that, at least in this experiment, learning the control, once you've learned a good representation, can be done by just training a very small number of parameters on top of having learned a very good representation of the world. Yeah?
So in this case, the control, like the representation is learned separately from the control, right?
Yeah, yeah, absolutely. Well, we'll see a lot of examples where that's not the case, but I think what's so interesting and surprising about this is that I would have not thought this would have worked so well. Like they essentially staged it, right? It's, you know, train the VAE. Once you're done training the VAE, you train a dynamics model, then you train your control. I mean, it's so surprising to me that this actually works, because you can imagine that, well, when you train your encoding, you'd pay attention to all kinds of things, but maybe not to the things that matter to predict the next state. Yeah. Because maybe there's, you know, the car is pretty small. How do you even pay attention to the car and so forth? Then you would imagine that maybe all the information that you care about will already have been erased by the time you try to learn your policy, but somehow, and this of course relates to the worlds that you're doing this in, and that's also why I think it's important to see the world. I'm pretty sure you can come up with environments where this wouldn't work. In fact, I emailed the author, David Ha, first author, last night. I said, well, it's really surprising this works. In general, it seems like it shouldn't work. And he said, yeah, I agree. In general, this maybe shouldn't work, but what we really want to see is, you know, if something this simple, if done nicely, what can it already do? And there's a bunch of follow-up work that will make this more complex than shown here. And that's why it's so important to look at the environment. So for the car driving, this happens to work. And we'll see another environment where it also works. And it's very surprising how well it works. Yeah?
So, I don't know anything about this environment. Does it always look like this?
It always looks like this, but the road can curve.
Okay. Because in that case, even a random policy gives you like all the different kinds of curves and all that stuff, right?
In terms of getting good data, good exploration, yeah. Exploration is not a huge challenge here.
Okay. So if you were to do this in like Mario, for example, then
Yeah, you will need to worry more about exploration probably. So on the left is an input frame. On the right is a reconstruction. So it's not perfect, but it's not bad either. On the left, okay, this actually we should show as a video. So let me go to the corresponding website. Get to the videos. So what we'll look at is, remember the architecture I showed, it takes in, there's a Z, which is the encoding of the image, but there's also the hidden state of the LSTM. And you can imagine a policy only takes in Z or takes in both Z and the hidden state of the LSTM, and we can compare how well that works. So let's see, start from the top here. So this is kind of showing some reconstructions. You can load a random screenshot, and you'll see on the right how well it reconstructs it. So the VAE does a pretty good job. I mean, it's not exactly matching pixel by pixel, but it's retaining relevant information, it seems. Then the RNN is trained on top of that, policy on top of that. Here is, ooh, that didn't work. Here is the car driving. So this is the environment in action. The little red and white things that you see, the VAE happens to never reconstruct those. So reconstruction here for the car driving environment, you see somehow it ignores the little turn thingies. But luckily they don't really matter for doing well in this environment. Then actual observations on the left, what gets encoded into Z on the right. Then after training a policy, so here's the learning in action. Initially it doesn't do all that well, but it learns over time what to do. So the top here is if you only get ZT. So if you only have Z, the encoding of the current image, you don't get past state. This is what you get. It means you don't get any notion of velocity of where you're moving. And of course, you're not going to have that smooth motion if you don't know where you've been moving recently. Here, if you also feed in HT, these are the policies it learns, and it's a much nicer kind of driving style. Then here is the kind of simple Doom environment. My understanding from all the videos here is that it's just one room. It's not a maze you have to navigate and take people out. It's just this one room. You got to try to take out the enemies on the other side. So they shoot things at you, which you got to avoid, and you got to take them out. For that environment, what I just described didn't really work. It wasn't enough to run RL in the real world. You need a lot more samples. So what they did is, since you build a simulator on the Z state, on the latent state, you can actually run really fast simulation in that latent space and run RL in the latent space, which is not perfect match to the real world, but since your agent only looks at Z and H, they're available there. And after you train, you get something like this. So here's the thing in action, and here's it in the actual environment, where actually, you know, it's doing some reasonable things. Then one thing that came up and that they had to do is in the simulated world, it learned to play some tricks that actually don't work in the real world. It was able to extinguish the fireballs, make them disappear in its dreams where it was simulating. In the real world, it didn't happen. But because it thought it could do it, it would get a lot of data in the real world where it gets killed by those fireballs actually coming at it. And then it'll update, do a retraining of the VAE, retraining of the model, and then retrain in the simulator to find a better policy. And after doing that a few times, it actually learns to do pretty well. And so what the cheating refers to here is that in principle, if your model is bad, you might find these solutions that you really don't want. But then luckily, whenever that happens, when you test in the real world, you get exposed and you get data that proves you wrong about what you've been doing. Yes?
So is the latent simulator like any like faster or more efficient than the lower?
Latent simulator is a lot faster. That's a big part of the benefit. So the latent simulator they run super fast. It's a fairly low dimensional latent state, and they can run simulation really, really fast.
But that's true of a lot of things, right? Like people say like, oh, Breakout has a ton of pixels, but you could compress it down to like way fewer pixels. So a lot of them are useless.
So probably you could do it. You could try it there too and see what happens.
Okay.
How did they learn the transitions?
How did it learn what?
The transitions?
The transitions are just an RNN. So there's an RNN that learns, that is trained to predict the, I think it's trained to predict an ZT plus 1 from HT and ZT and the action. So there is some loss somewhere on here. Here it is. So P ZT plus 1 given AT, ZT, and HT.
In practice, how many of the previous frames do you really need to succeed?
How many of the previous frames do you need to succeed? Let's say if you did not train an RNN, but instead you just did the next frame prediction based on, let's say, the past 2 or 3 frames.
Yeah.
That's a good question. I don't know if they tried out anything like that. Yeah. Usually that's a pretty good alternative to an RNN, is to just look back a few frames. I mean, we've seen many examples. Essentially, all the autoregressive models in some sense are also like that. They look at all the past to predict the next rather than having a hidden state.
How can we make sure that all the states are as visited before you do the actual simulation in the real environment?
How to make sure you visited all the states?
Because they have to collect all the states data to train the world models. If you miss some part of
Yeah, it's a good question. How do you make sure your data collection is comprehensive enough? That's kind of just a standard RL problem, how to make sure you have enough exploration. Yeah, it's a good challenge. I don't want to dive into that here. I mean, we can teach a whole 2-semester course in RL and so forth. But yeah, it's an important question. Okay, so we watched the videos on the blog site that are in the slides here. They also then did something with control, and it kind of goes to your question a little bit, where they had to pay more attention to exploration, because if you just do random things in this kind of pendulum swing up environment, you don't get very interesting data, and so you don't learn to do it. But then if you repeatedly learn in simulation, you don't do so well, you collect new data, keep repeating this over time, it does get enough data to actually succeed in the real ground truth simulator. David said some of the things that address the challenge that we just initially talked about here, which is if you first train the VAE and then everything else, maybe you already lost some things. Here are 3 references he sent along he thought would be good to look at. We'll cover some of those later, but those are the 3 he highlighted in that specific context. We looked at the demo already, so let's go to the next idea. Okay, so we've gone from observation to state and hoped for the best. You might maybe say, why don't we, at the same time as we learn a mapping from observation to state, also learn a mapping from state and action to next state? That way we're ensuring that what we put in the state is enough to predict things about the future, and we don't lose something critical about the future. So a bunch of work goes in that direction. One of the kind of early successes is called Embed to Control. So in this work, just like before, we'll encode a visual state to some latent state. Then while training this, you'll also train the mapping from ZT to ZT plus 1 and so forth. And you assume you have access to the actions. So you'll have a rollout with actions and observations, and you're supposed to be able to learn the dynamics model at the same time as the encoding. You might say, how do you supervise this one? How do you know what ZT plus 1 is? Same thing. You'll have an observation here. And the observation will get encoded. And you need to learn the mapping along these arrows. So that should in principle address that first question of, okay, maybe we lost too much information, we should learn the model at the same time. Part of the motivation here also was a second aspect, which is that there are problems that are easy to solve. What do I mean with that? In general, a Markov decision process is hard to solve. But if it's a linear control problem, it's easy to solve. So can we force it to be such that we find an embedding such that in the embedding space, things are linear? Because if that's the case, then the problem becomes easy to solve. And if you want to force the dynamics to be linear, well, you better learn the dynamics at the same time as you learn your embedding. Otherwise, chances are very low that you end up with an embedding where your dynamics end up being linear. So there's kind of two things at play here. One, make sure you don't lose information by learning the encoder first and only later dynamics. And two, by learning dynamics at the same time, we can force that to be simple and have the control solution be very easy. So in this work, Embed the control, once they learn the embedding and dynamics model, solving the problem is just standard optimal control, and you get the solution right out of it. You don't need to run any RL, nothing. It just directly solved within optimization. Okay, they tested this on pendulum, card pull, and 3-link arm. And the stochastic optimal control in the latent space, what did they do there? I think they did a LQR. The details don't really matter, but if you want to learn more about it, maybe take 287 in the fall or go read the notes from a previous offering. But essentially, it's a method that is very well established since many, many decades ago as a way to solve optimal control problems when you have a linear dynamical system and a quadratic reward function. So they learn models that are linear. They learn stochastic models, so actually they say the next hidden state will be a linear function of the current hidden state and the controls with some Gaussian noise around it. And that's exactly the scenario in which LQR will work and will give you essentially a closed form dynamic programming solution. Okay, so ILQR is the kind of iterative LQR method that can solve the problems when maybe you need to do a few iterations before you get the solution because the system's not actually perfectly linear, it's close to linear. All right, so to capture enough information about the state, you got to set up a encoding, a decoding, and a dynamics model. To make sure that you have good long-term prediction of latent state, you might want to have some loss on longer-term prediction. But that come back later also. Often what can happen if you're not careful is you learn a simulator, and it's good for one step, but if you run that simulator for 20 steps, it's actually doing really bad. Why would that happen? Because you learn to predict only for one step. And the way you learn to predict is you learn to predict from something that you saw. You learn to predict from an encoding that you got from real data to the next encoding from real data. But then once you make your one-step prediction, the ZT plus 1 you end up with might be out of distribution because you don't predict perfectly. And so it might be slightly out of distribution. And when you now apply your next state predictor on the slightly out of distribution ZT plus 1, it might not do so well. It might be even a bit worse. And this will repeat over time, and you'll get some divergence. So you want to be a little careful. So you might want to put some kind of loss on keeping the latent states kind of together, maybe coming from a Gaussian. And then you want it to be all linearizable. Okay, flipping through this VAE, you know about how that works, so we don't need to kind of redo that. Locally linear latent state space model, that's just linear regression effectively that you put in there from ZT to ZT plus 1. And here's the total kind of setup that you end up with. Once you have that trained, you can then run optimal control to find optimal sequence of actions. Once you find the optimal sequence of actions, you execute the first action, you see what the result is, and you rerun optimal control and find again the optimal sequence of actions, execute the first one and repeat. That's called model predictive control. Okay, so let's look at some results here. Full model. Here is their card pull balancing. So that's one of the tasks they look at. It works reasonably well. It was one of the first results on learning to control these kind of systems from pixels. And here are some of the kind of numerical results. Rather than diving into specifics here, I want to highlight some kind of maybe limitations you might think of. Actually, let's watch a video of this in action so you know where it works, and then we'll talk about limitations and extension. So here's a planar system. So it's a navigation task. And it's a kind of simple, like, I think it's a point mass navigation task here. And you can see that an embedding is being learned, in which control should be easier. Swing up, real image on the left, generated prediction on the right. And you can see it indeed learned how to do swing up. Card pull balancing, it also learned how to do. I mean, obviously the imagery here is relatively simple, and the actual tasks underneath are fairly low dimensional, 2 or 3 or 4 or 5 degrees of freedom. 3 link arm, how to reach a goal state. For robot arms, it's very well understood how you go to a goal state. That control problem is straightforward, but the challenge here is that you don't get the state of the arm, you get images. And what happens is that indeed it learns a good underlying representation. If you, in the underlying representation, run optimal control, you succeed at the task. Now, where might this not work so well? Well, if your dynamics is not really that linear, then you might have to make some decisions. You might say, well, I don't want just a linear model, I want maybe a sequence of linear models. But if you have a sequence of linear models, well, what might happen now is that maybe they vary a lot over time, and you might have a pretty poorly conditioned problem. Or you might say, I'm going to just approximate with a single linear model, but then it might not be a good approximation. And so some recent work, actually Marvin, who's in the class here, has done, called Solar, looks at extending this to when you want to fit locally linear models, but the locally linear models should come from some kind of joint distribution, so you have some natural regularization across the linear models that you'll encounter along your trajectory. So it regularizes the linear models you will end up with by learning them all in one go, coming from the same prior. Here's a little bit of detail on how this works, but essentially the same kind of setup, but with very good regularization on the local linear models you end up with. And what you get is actually a robot that, from image observations, shown on the right here, is able to control itself and stack a Lego block. Only 5 minutes of training so far, it's already doing pretty well. After 10 minutes, it's pretty much there, getting into the correct spot. And so, of course, the imagery here is a lot more complex. The encoders and decoders need to learn are a lot more complex for this to succeed. So this is a pretty good proof that this might be a method that, maybe might work on pretty complex scenery of your own.
Pieter,
Yeah.
Goal
Is this what?
Does this give a goal image and optimizes the data?
Oh, we should ask Marvin. Marvin, how is the goal specified here?
This is just a reward.
There is a reward.
There's a reward function based on like the end effector position. There's another task with pushing where you use a goal image.
I see. So some incarnations with goal images, some of them with an actual reward function that's available.
I guess the main point is that it's not important to the method.
Cool. So you might actually want to, within this kind of notion, there is quite a bit of work. And so what I'm going to do in the next ones is go one slide per method to just give you the quick high-level idea. We're not going to dive into the details, but that gives you some notion of what people have tried. What's another thing you might want to do is, let's say you have a bunch of convolutional filters processing an image, and you care about this underlying latent state. Well, one way to think of your conv filters is that they might detect certain objects. And if you think that they detect certain objects, then you might say, well, my conv filter at the very end for maybe, I don't know, Lego block, should tell me where the Lego block is. And so instead of just putting a fully connected layer after that, it's got to figure out what to do with all of this, which would introduce a lot of parameters, you could instead introduce something called spatial softmax. And what it does, it essentially looks at your image, the activation map, and on the activation map says, where is this filter most activated, and passes those coordinates on. So it's a massive reduction in dimensionality in some kind of clever way that you can go from, well, maybe you have, in this case, 16 high-level filter responses. Each is 100 by 100 roughly, so that's 16 times 10,000, so that's 160,000 numbers that are coming out at the end there, and you turn it into just 32 coordinates. And then your control system can learn off of those 32 coordinates rather than off the original filter responses. So here's this system in action. It's collecting data here. Based on this data, it's training a spatial autoencoder, which actually does all this, and then after the coordinates, expands it back out to reconstruct the image. Once it's done that, it'll then take an image of a goal configuration, know what the feature values are for that goal configuration, use distance in that feature space as reward to then train to try to get the block to that matching configuration. Mm-hmm.
Like a very, very trivial question. So it seems like it's reconstructing a downsample version of itself, right? Like taking a 240 cross something, getting to 60 cross and 60.
Yep. Mm-hmm.
So that if it's just an autoencoder, then it would just encode. It's basically going to behave like a CV2.reshape, right? Basically, like it's just going to be like a image preprocessing function that the representation.
So you mean this part or this part?
Yeah, so the final reconstructed version,
Mm-hmm.
you're posing it to be a smaller version of the input, right?
Yes. Mm-hmm.
That means it just naively encode what's needed to get all the details right in the It basically just functionally mimic a image preprocessing pipeline that just does like some nearest neighbor downsampling or something.
So, I mean, it sounds like your question ties into why does it go in as 240 by 240 and come out as 60 by 60?
Yeah.
So, it's a good question. I think one reason let's say you go to 60 by 60 at the end is to kind of, maybe you say, most of the things I care about when I do my feature learning can be seen in a 60 by 60 image, but so I don't really need the 240 by 240. But maybe when you do control, you still want higher resolution. So you still want to learn to kind of get the coordinates out from a higher resolution image to get higher resolution coordinates out than you would get from right away going from 60 by 60 back to 60 by 60. That'd probably be the reason. We'll see some other funny losses later that don't exactly look at the original pixel reconstruction also. Here's another one. Kind of a somewhat crazy idea maybe, but apparently it kind of works. So they said, how about instead of training an encoder and a decoder, let's just train an encoder. You might say, how's it even possible? Well, how are you going to retain anything about the world if all you do is train an encoder? It's just going to make everything zero. You're good to go. You have encoded and nobody's going to complain about it. But even though you don't need to reconstruct, they introduce a bunch of other losses that they say they know matter in robotic settings and have to be true about your latent state. So you turn your observation into a latent state. There's the velocity part of the state. So there's a position part of the state, the velocity part, which has to be the difference of position between two time frames. So they say in robotics we have position and velocity. Then what we're going to do is instead of letting this just be zero, because we don't need to reconstruct, so you could in principle do anything, first of all there should be variation. So you collect a bunch of data and there's an objective that moves all your encodings as far apart as possible. So now they're all moving apart. So you're not just collapsing onto zero. Then another way to give meaning to them, they don't just all move far apart and are in different places, but they're somewhat related in meaningful ways, is that slowness on position. The encoding at time t for position should be close to the encoding at time t minus 1. Same for velocity. Because systems have inertia, velocities don't change that quickly, so the velocity at time t and t minus 1 should be close. Then it turns out that, I mean, in robotics you might have something that just bounces off the ground. And so the velocity will have totally changed, but the magnitude of the velocity still stays the same because of conservation of energy. And so they said, well, we want to regularize on the magnitude of the velocity to allow for things that bounce off of other things. Then There is controllability, which says that they want a high correlation between actions you take and your next state. Okay? So, because if your actions don't affect your next state, then probably the representation that you're learning is not that meaningful. And then they actually did some pretty convincing experiments with these environments, also going from pixel values to then be able to control in the latent space, directly in latent space, these systems. Yes?
So instead of having different losses on velocity and inertia and all of these things, would it be possible to just have sort of a loss on like the Hamiltonian system or something of that form?
That's a good question. I mean, the question is, well, are there other options here that might be related to, if you had some kind of notion of what would the Hamiltonian or more generally maybe kind of a, energy description of your robotic system look like? Yeah, if you can come up with other terms, why not? If you can put in there conservation of energy, why not? Those all seem good ideas. Sometimes it's not that easy to put them in, especially if you don't know what you're going to deal with. If you have different systems that you're trying to control, is the same loss going to apply to all of them? Are you going to hand tune it to each one of them because you know a little more about this one or that one? So yeah, it depends. But that's the spirit of this work, is that there are some things we know about the world that we can impose on our feature space and feature space dynamics. Might as well do it and get better results that way.
Questions for the conservation?
Sure.
You mean the energy, so it should be V squared.
Well, I took this from the paper. This is what they did. They said we like to retain the magnitude. I mean, apparently it works. I think there's a lot of choices there that you can make. You could think of it as maybe something slightly different, like impulse or something, conservation. But this is the equation they use.
Okay. Thank you.
How is the degeneracy avoided here?
The degeneracy is avoided by the very first term. So this term here is trying to push everything as far apart as possible. So if you look at this is state encoding, another state encoding. If this is small, the difference, then this e to the negative, the small thing, will actually be a high number. As if this is big, this will become small. So you want to make this as big as possible. And so this loss term, it's the only one. But this is the one that ensures things get pushed apart. Okay, here's another one. Darla. What's done here is a VAE is trained, variational autoencoder is trained. Observation goes in, gets embedded, gets decoded to X hat. A normal autoencoder would just do that and you'd be done. That's what you train. They have this beta VAE. What it means is that you put extra emphasis on the prior. And the prior is a Gaussian. And if you do that, all the variables are independent in the Gaussian. And so this might lead to a representation that generalizes better somehow. That's the thinking. And the experiments do show that. So this might lead to a better latent representation that might generalize better because you train independent variable latent representation. Then we talked about reconstructing all the pixels, reconstructing only a downsampled version of the initial pixel set. What they do is they actually train a deterministic autoencoder ahead of time, separately from the VAE. Train a deterministic autoencoder, or a denoising autoencoder. They train a denoising autoencoder and use the denoising autoencoder to encode both the reconstruction X hat and the original X, encode, decode, and see how far apart the denoised versions of X and X hat are. So rather than differencing X and X hat right away, you pass them both through a denoising autoencoder before comparing them. And that's to be less sensitive to very particulars about the pixels and be somehow caring more about the overall structure of the image. So that's how you train your representation. Then the policy is using the latent state. So there's policy here using latent state. Then what they look at in their experiments is, this is kind of cool. They use DQN, but DQN can be trained directly on the original images or it can be done with the architecture I just showed. Here's Darla. And they'll both do about the same. You don't expect much difference here because this is the training environment. But then the hope is that Darla transfers better because it learns a representation that's more invariant than if all you learn about is just about maximizing reward. And so what we're seeing here is that original DQN is not that good at collecting reward in this new environment, but Darla has learned some more kind of more general underlying principles and is more consistently collecting reward in the new environment. Let's see. Causal infoGAN. Oh. So causal infoGAN is another way to try to understand the latent space dynamics and to be able to then do things in latent space. So rather than using a VAE, here we have two observations. They both get encoded. They're consecutive observations. They get encoded. You learn a dynamics model to go from one to the next. Then once you have two, the first one, next one, you feed them through a generator, which will lead to fake observation pair. And the discriminator is supposed to decide whether a sequence of two observations is real or fake. Here's a comparison. This is causal infoGAN. This is a rope data set. So a rope has been moved around. And the question is it realistic to see a sequence of images for a rope? When you train a regular GAN or DC GAN, infoGAN and DC GAN are two comparisons here. You go from first frame to last frame, and you just interpolate in the latent space. You'll see you go through states that don't really make sense as intermediate states if you think about the dynamics of how a rope works. Because they don't know about dynamics. They're just trained on single frames at a time. With causal infoGAN, by training on pairs of frames that are consecutive, it learns to embed in a space where you understand the dynamics of the system and the interpolations are actually meaningful. And then on top of that, you can start designing control algorithms. Because now you can say, if I want to go from here to here, all I need to do is interpolate in latent space, generate the sequence of images, and then I can do control onto the next image, onto the next image, which are small steps from where you are. And it's often easier to learn to control for that than to learn to control for a very long horizon. Yes?
The generator doesn't actually take in the real observations as input, right?
The generator takes in a encoding. So generator takes in a encoding. So S is an encoding of a real observation here. Or it could. You can choose. You can either take in the ones from the actual observation, or you can sample it from a Gaussian if you ensure that this comes from a Gaussian. Yes?
What's going on with the mutual information there?
The mutual information part, that's just ensuring that you actually have an encoder. So standard GANs don't have encoders. Standard GANs essentially just go from noise to generation to discrimination, and that's it. And the mutual information is ensuring that you encode from observation back into the code. Here's another one, Planet. This is one that I mentioned earlier with when we were covering the world models and one of the kind of future works that might do a little better, slightly more complicated problems. So what's happening here? You still learn an encoding. You at the same time learn a latent space dynamics model for it, but you train it with multi-step prediction. This is to ensure you don't get this divergence when you simulate in latent space, that you don't kind of, after many steps, are in a part of space that you would never be when you encode real-world states. So you have a loss function that's not just on predicting one step ahead, but predicting many steps ahead. And they have some math around that, how you do that with variational lower bounds to get that to work out nicely. And then this one is doing planning rather than reinforcement learning to control itself. So you can, once you have a simulator, instead of learning a control, you could also just plan ahead, try a few sequences of actions, see which one might be the best, execute that, and repeat. And so here are some example successes for Planet. Here's another line of work that kind of cares a little less about the latent state and says, well, if we could do perfect video prediction or really good video prediction, that should actually be enough to control our systems. Because if you have perfect video prediction, then you can think about, okay, for this sequence of actions, what will I see? For this other sequence of actions, what will I see? And then you pick a sequence of actions that gives you the result that you want. And so a lot of this work is happening here at Berkeley, Chelsea Finn, Sergey Levin, Frederick Ebert, and so forth. And so there is a current frame to next frame prediction model, action conditioned. And if you train it up on enough data, and the beauty is that you can collect this data by just robots running all the time, collecting their own data. You can have them do some pretty basic motions that interact with objects in a bin. And then after you've trained up the model, you can do look ahead. Of course, a little expensive to do this kind of look ahead, because if you want to look ahead, I don't know, 100 steps with this, you got to do a video prediction over 100 steps. So often the horizons for this are a little shorter, but it's actually capable of doing quite complicated tasks. If you look here, here at the bottom is what the goal is. This pixel should move over here, and for that pixel to move over there, it knows that it should pick up that thing and go place it over there. Okay, and this is just because it has a video prediction model and knows that that's a sequence of action that will lead to the desired result. Here, this pixel has to go over there. It knows it has to pick up this and move it over there. Here, the apple has to be placed on the plate, and so it goes from there to here. But again, the apple has to go on the plate is just specified as click on a pixel on the apple and draw an arrow to where it's supposed to end up. And then here, the sleeve of this sweater is supposed to end up at the bottom here by clicking on the end of the sleeve and clicking at the bottom there, and it knows that that's what it's supposed to do. It's just by thinking through many possible sequences of actions, and some of them lead to that kind of result, and that's the one it will then take.
I don't know if there's time, but could you elaborate a little bit about that whole arrow that you draw and how it knows that it's actually supposed to do?
Oh, so the question is, how is it being specified what it's supposed to do? So that actually ties back into some specifics of how the video prediction model is set up. So the video prediction model here is set up in a way that it actually keeps track of where things move. So under the hood, it has a notion of where pixels are moving. And if it knows where a pixel is moving, then you can actually specify things by saying, I want this pixel to end up over there. And so that's what's happening. If you just had a black box prediction, then it's not clear how you would give this way of specifying what you want. But because there is this transformation here, is effectively saying where each pixel is moving. And so that's how you keep track and how you can specify the task. There are other things you can do. If you don't have this kind of transformation model, other things you can do is you could give a goal image instead of a pixel motion. You say, this is what I want to see at the end. And then you don't need that assumption. You can just do any kind of video prediction. And with any video prediction, you can say which sequence of actions will lead to a video that leads to a frame that's very close to the target frame. But if you want to do it on a pixel level like is done here, you actually would need to have some kind of notion of tracking where they go.
Is the reward based on pixel distance in that case? If you give a goal image?
I believe it is, yeah. I'm going to skip to the next thing, actually, because I want to cover a lot of things and not keep going on any single thing for too long. So here's another idea. Imagine you try to work with glass bottles, and you try to build your video prediction model, and you drop something, and it's like glass is shattering everywhere, there's water going everywhere, and it might take a long time to train your video prediction model to predict this correctly. In fact, it might take a really long time before you get this to work really well. Might not even be possible with the current models that people have. But if you think about it, when you think about what you actually want, do you really care? I mean, do you ever think about when I drop a water bottle on the ground, how everything's going to fall apart? No, you just say, it's going to break, it's a bad outcome. That's enough. And so the question is maybe not so much, can we simulate all these details, but can we capture enough high-level information to get the job done that we want to get done? And so that then ties back to wanting to do video prediction in some ways, but not necessarily video prediction, but prediction in the latent space. And so you have a latent space encoding of the nice bottle, and that's not broken yet, a latent space representation here, and you want to be able to predict that if you take an action that drops the thing, you end up in the latent state over here that you maybe don't like. How do you train one of these models? Let's see. Oh, got to go back. So if you want to predict in latent space, and all you do is you say, I want to do a really good prediction job in latent space. Again, the challenge becomes just make everything 0. Everything's 0, you can predict the next 0 really, really well, and it's trivial. So how do you avoid that? The way it's being avoided is because the latent space will need to be able to solve 2 tasks. You need to be able to go from current latent state in action to the next latent state, but also from latent state at time t and latent state at time t plus 1. You need to be able to predict the action that was taken in between. This is often called an inverse dynamics model. So you train both a forward dynamics model going from zt and at to zt plus 1, and an inverse dynamics model going from zt plus 1 and zt to the action that got you there. That ensures your latent space is not degenerate. It also ensures that your latent space focuses on things that you control. And that kind of also goes back to the very first example, the Unreal example, where using Q functions, which makes you focus in representation learning on things you control and what you might be able to control how well, versus just learning next state or next pixel prediction. Same thing here, focus on what you can control. On the left is the data collection, if it's willing to play. Okay, on the left is the data collection. And so what you see here is the robot is supposed to poke. And so the data collection is just a scripted thing that says, detect roughly where an object is, move near the object, and make a motion that pokes it in some direction, and learn from that this kind of latent space model of how the world works. Then once you have that, you have a current state and a goal state. You can then, in latent space, try to find out what sequence of actions will bring you the closest to this goal state. In fact, here is just done in a greedy way. It's just looking for which action will bring the latent state the closest to the latent state that's the goal state. And just repeatedly do that till it's close enough to the goal state and declare success.
Here, did it generalize the background?
Here it's always in the same background, I think. So. Oh, so this is a later experiment. So initial experiments were with green background, and then the later experiments, also the training data collection was done in the bins, so the objects don't fall on the ground, which makes it a lot harder to collect a lot of data. Because this robot was running overnight, 24/7 collecting data, and so we need to design something that keeps the objects in the bin rather than just a table where they sometimes disappear, and next morning you realize the robot didn't collect much data because the object had already disappeared onto the floor. Let's see. So the things we looked at so far are about observation to state, maybe including something about next state, but actually what you really care about is rewards. And so maybe to learn better representations, you should keep that into account from the beginning. So here's a couple of example works that do this. Predictron. What they look at is, can you predict? So the neural network needs to learn a model that predicts all the future rewards you're going to get for a given current action or sequence of actions. So you're not asked to predict frames, you're just asked to predict rewards for all future times or averaged over all future times. In this particular case, they tested it in maze navigation and in billiards. So somewhat constrained environments. There's some limitations to just predicting rewards you're going to get. But here, if it's not connected from start to goal, then that's a case where you're going to get no reward. If there is a connection, you're going to get reward. And so effectively what it learns is to discover whether or not there's a path from start to goal. For billiards, it's about getting a ball into the pocket. And it's essentially saying, if I were to take a certain action, what is the prediction of reward in the future? And then you can loop over many, many possible actions and say, okay, which action will lead to the higher reward? Keep in mind, though, that in billiards, you only take one action at the beginning. And that's in some sense a bit the kind of, this is early work from a while ago, but a bit the limitation. There's a current state, there's one action you're going to take, and then there's a prediction of rewards that will happen in the future. And there's no notion of action after that, after that, after that. It's just a one-shot thing, and predicting rewards. Yeah.
So outside of this paper specifically, why would we care about predicting all the future rewards rather than just learning the Q function if we're just going to use it in an argmax anyways?
It's a good question. Why would you care about predicting future rewards? Because it seems like it's already kind of very narrow. I mean, you're back to just predicting the cherry on the cake rather than predicting a wide range of things. I think where it gets interesting is the next one, which is where the way you do it is you actually think of there being many possible rewards. We call them, they're called features here, successor features, but it's as if you had many reward functions. And for every possible reward function, you want to predict how much reward you're going to get under your current policy. And that's like a lot like the pixel control in Unreal. It's very related, where every pixel could be seen as constituting its own reward function that it'll provide. But you can have a wide range of reward functions you define. And then also if you have a new reward function that's a weighted combination of one of those past ones, you might be able to combine them together in a weighted sum to get, at least on policy, this will work. You can take a weighted sum on policy of expected rewards. And so what this effectively does is, if you have some insight about rewards that might matter in the world, it gives you a way to control the system to pay attention to what might matter in the world, let's say objects or doors, openings, rather than focus on pixels, which might not ultimately matter as much as rewards that you already have in mind that could matter. Yeah.
So this is literally the Q function.
Yeah, they're learning many Q functions in parallel here, is the idea.
So how is learning many Q functions in parallel different than learning the Q function of like a weighted linear combination of all those things you care about? Like, why wouldn't you just change? You'll
have more loss functions, is the idea. So, and another place where this comes back is, let's say, distributional Q learning. In distributional Q learning, you learn a histogram over rewards you might get in the future, rather than just expected reward. And what it does, I mean, it does many things. One of the things it does is sometimes you get a reward of 100, sometimes a reward of 1, because maybe sometimes you do something big, sometimes something small reward. In distributional Q learning, you need to understand that notion that sometimes it's a big event, sometimes a small event, and that's very related to this notion here. There's many features contributing, and you're going to force yourself to learn about the future of every one of those features independently. Then still you can combine them, but you get more signal by decomposing your reward. And that's in distributional Q learning, that's by binning it. Being in a different bin makes it different. Here it's being a separate axis that you learn about. Yeah.
So is this kind of like using an ensemble to approximate the distribution?
Is this an ensemble to approximate the distribution? I wouldn't say so. This is about having many possible objectives. Let's say, imagine you had one objective you cared about. It was a sum of many things. If you only look at the sum ever, the amount of signal you get is much less than if you always looked at each one of them individually and tried to predict each one of them individually. So it's a bit like, okay, maybe you're an agent collecting apples, cherries, cucumbers, getting negative rewards from running into some bad things. There's a bunch of stuff in the maze that you need to deal with. And if you only learn about everything summed together, the amount of signal you get is much less than if you learn about, I expect to get 5 apples in the next 20 time steps, I expect to get 2 cucumbers, and so forth. And so that it's about getting extra signal. Then some work done at Berkeley here looks at essentially predicting many, many things, many steps into the future very explicitly. So it's led by Greg Kahn. And so the idea here is that when you have current images coming in, so you have your recent images, so no, let's say, process them, you still have a recurrent neural network. You still want to optimize reward, but actually to do representation learning, what's happening is it's thinking about many features it wants to predict. For example, it might want to predict, am I going to have a door on the right of me 1 step down the line, 2 steps down the line? This for the experiments here are with a robot that navigates hallways in our buildings here, for example, Quarry Hall. And so will I have a door next to me? Will I have an open door next to me? Will I have maybe a wall next to me? Will I have open space next to me? And so you can, ahead of time, if you want to, essentially define a bunch of image classifiers or feature extractors. You can imagine you just take something, you train, you have some feature extractors, and now you want to predict how much those feature extractors will fire or not fire every future step. And that gives you a signal about things that are higher level than just predicting whether a pixel will take on a certain value. So it's very related to the pixel prediction, but it's doing it at a feature level here rather than pixel level. Here is the robot in action. Let's see if I can get this to play. So let's not play the whole thing, but let's look at the experiments at the end here. So here it is, having learned to navigate in Carla. Carla is a self-driving car simulator environment. It's learned to kind of stay on the road. And it essentially has events. There's an event of collision, an event of hitting a certain speed, event of having a certain heading, event of seeing a lane or a change in lane. And it's learned to predict against those to learn a representation that's good for then achieving its task. Let's look at the real robot. So this is the real robot collecting data and doing essentially training that network to predict many types of events that it might encounter in the future. And then once it has that, it can use that to plan against it to maximize reward. Let's take a look at the robot navigating. On the left is the proposed approach. You can see it avoids collisions. It also likes to be close to doors. That's an event that it gets rewarded for, but it should still not collide with the doors. Yes?
So is it learning the task of, is there going to be a door next to me in the next time step alongside learning move towards doors?
It's learning, is there going to be such a thing next to me if I take this sequence of actions? And it's using that as a simulator to decide on what sequence of actions to take to maximize the reward. And we can change the reward on it. So we can say, let's reward for being close to doors, but also for not having collisions. Or we might reward for having collisions. And so it's learning to predict against all of those possible things it might care about. And then we can specify after the fact which one to care about now.
So it learns the simulator like first?
It learns the simulator first, correct. Well, it learns it's not a full simulator in that it doesn't learn to simulate the world visually fully. It learns to simulate which features will be active in the future as a function of what actions it takes.
But there's no way that it would get biased to like oscillate in front of like a door to try and maximize reward on the task of predicting whether a door is going to be in front of me in the next frame by just going like backwards and forwards in front of the door.
No, the training of the predictor is separate of the maximizing reward, correct. Okay, so you might actually ask yourself the question, with all the things we've looked at, and I mean, everybody runs experiments in different environments, it's hard to compare. Might there be some optimal representations? Let's take a break, and then after the break, let's look at how we could think about optimal representations. All right, let's restart. So we've seen a lot of ways of turning observations into some kind of representation. And it's not really easy to know which one's better or worse, and the experiments tend to be on different environments. Some look more difficult, some maybe look a little easier, but still pretty hard to really think that through. So one thing you could do is, well, maybe we could just do more careful benchmarking, and I think that's pretty valuable to benchmark those things more directly. But you could also ask the question theoretically, can we get some optimal representations, and what would it even mean? So here are some references. And they're actually mostly from before people started doing deep learning. But in these references, what people look at is this notion that I have a Markov decision process. And it's in some very high dimensional space. But intrinsically, there's something low dimensional that matches up with it. Then, in principle, there's something called a homomorphism that maps one to the other and can map it back. And if I can find that homeomorphism between the two, then I have what is called a bisimulation, where I can simulate in one or in the other, and there'll be two simulators that run perfectly in parallel. And so if you can build a bisimulation or homeomorphism, then you might be able to guarantee that the world you're now simulating in matches the real world that you want to solve well enough, and then whatever solution you find in the simulated one will match the real world. And so there's a bunch of work going in that direction, thinking about, okay, how to build a proper bias simulation for a more complex environment. Now, there's another paper that I want to draw your attention to, which is called Separation Principle for Control in the Age of Deep Learning. So let's maybe first talk about what does it mean to have a separation principle for control. So in classical control, typically people don't take images as inputs, but they might take still some sensory readings as inputs. And those sensory readings are not exact state readings. They are a noisy version of state or some projected version of state. And by having many readings over time, you might be able to reconstruct the state, underlying state of the system. And the separation principle in control, what it means is that you can take a sequence of sensory readings, turn them into something that we call state. And that state is enough to then do control on. You don't need to refer back to the original sensory readings. And so what that means is that you can build two things independently. You can build a state estimator and you can build a control system separately from each other without interaction. And if you build a perfect state estimator, then build a perfect controller, combine them together, they will do the job. And so the question is there something similar you can do in the age of deep learning where you might have this like million-dimensional pixel stream coming in, and then you try to make sense of that and do control based on it. It's not so clear, but this paper tries to get some insights into it, and kind of the high-level gist is that it looks at this notion of information bottleneck. And so the idea here is that if you have information that lives in a continuous space, a high-dimensional vector, and if you're allowed to put noise on it and pass on the noisy version, then in some sense you erase some information, you compressed the original input into something new where it's tolerant to that kind of noise. Much like in a variational autoencoder, you embed, you're allowed to add some Gaussian noise before you decode. Same thing here. And so the information bottleneck principle ties into this notion of how you might be able to have a separation principle for control in the age of deep learning, where you take sensory observations, and then ultimately you retain sufficient information, but minimal, but sufficient to do control with. And so that's the idea here really is, how do you erase as much information as possible from your input while still having all the information you need to do planning or control? Very recent work, I wouldn't say it's like fully conversion. People know exactly how to do this, but I think it's a pretty promising direction.
So in some practical sense, are you aware of any successes in robotics apart from like Josh Tobin's work, where like the control part and the perception part is totally, disentangled? Like the domain randomization does the perception part, and then the one-shot limitation does the control part, right?
Yeah, so the question is, how about some successes in robotics where there is a separation principle? I think it's actually true in many, many scenarios. By default, many people try to separate things. For example, if you essentially, whenever you train some visual representation and then use it as is without backpropagating into it while you're learning for control, you're already doing this. It might not be a perfect separation that you want, but you actually have separated things. And so a lot of people will build a vision system, have the vision system output some information, and then do control on top of it. A good example is self-driving cars. Like pretty much all self-driving car systems, you go from image to semantic segmentation, and you assume that the semantic segmentation is the thing you then use to make decisions based on. And if that's what you do, you make your decisions based on semantic segmentation, you essentially have defined your separation between estimation and control. Your estimation output is still high dimensional. It's still an image. Every pixel is annotated with what's in it, but it is a separation from the original pixel values to how you actually do control on top of it.
So in some sense, the segmentation is like the best kind of practically realizable visual information space between the raw pixels and the latent space.
Could you rephrase that?
So in some sense, like something like segmentation space is our best hope for something that retains all the information from the raw pixels, but still is good enough for running some.
Yeah, so that's a good question, I guess. And I mean, maybe I don't think this paper looks at these kind of specific settings. It's more very abstract and a high-level theoretical work. But in principle, could try to measure what's the mutual information between the original pixel values and what's in the semantic segmentation. And, well, how much information you lost. And if you lost a lot of information, then you did a good job according to this objective, assuming that semantic segmentation is still enough to make your decisions from it. You can also wonder, why not just learn it all end to end? Why not just learn a representation that's good for planning, rather than all the things we described so far? If we know we're going to plan or learn against it, can we somehow phrase it directly that way? What would that mean? What would that be like? Well, maybe you know that there's this planning algorithm called value iteration. And value iteration can make exact plans, exact optimal plans, if your state space is small enough. And this kind of goes also a little back to the embed to control, where we knew if we had a representation that was linear dynamical system, we could find an optimal controller easily. Same thing here. If we can find a discrete space that's relatively low dimensional, then we can run value iteration on that discrete space to find an optimal solution to the problem. And so in value iteration networks, that's how the problem is phrased. The problem is phrased as you have sensory inputs, you will process them into something new. In that new space, which you can choose what it is because you get to learn the encoding into that new space. In that new space, you're going to run value iteration. And the result of that value iteration should be an optimal plan. You can supervise this with demonstrations. Or you can do reinforcement learning this way and do it against rewards. But the simplest way to test something like this, you have demonstrations of, let's say, optimal plans. And then you just see, well, what encoding results in, when I run value iteration, in something that matches with the demonstration I saw. You can backpropagate through the whole thing and find a representation that's great for value iteration. Not everything can be done with value iteration. And actually, this is a motivating slide from Aravind from a while ago. So this kind of goes a little bit back to the bottle with water that's falling and splashing apart. And you know, if you do any kind of reconstruction kind of error, you'll be paying attention to every single pixel in this image and try to get all of it. But if you're sitting in front of a white noise TV or whatever, reconstructing all of that might just be a total waste of your time. So, according to Aravind, this is the answer to you. Enough of pixel reconstruction error. What we actually need to do is learn something that is good for later doing planning. We already covered the value iteration, but there's a little bit more detail here. So what does it look like? You have an observation. You feed it into this box. This embeds it in a discrete space on which you run value iteration, which looks like this. It's like Bellman backups and so forth. You run a few loops of that. That's really, you can encode it in a recurrent neural net, so you can backpropagate right through it. Value iteration runs here. Out comes the optimal value function. Then you have an attention that looks at the value function coming out in the current state, decides based on that what to do, and this should be the optimal action in that state. If that's true, then this embedding here was a good embedding. And then the lower dimensional, of course, you can make this, the more you're compressing your state while still making optimal decisions. So that's one way to do it. Environments in which we tested this was environments shown earlier here. So some grade well navigation tasks. This is actually imagery from Mars. This is the surface of Mars, and to find optimal paths for a Mars rover to navigate the Mars surface, and also some continuous navigation problems. A lot of things are not embeddable in a small discrete space though. So here's some other idea. Aravind is the first author on this paper. It's called Universal Planning Networks. And we're going to actually optimize this entire thing end to end. But let's break down what's inside of it. What's inside of it is that we have an observation. We want to be able to encode, maybe decode, but definitely want to be able to encode this observation into a latent state. We want to have a dynamics model in latent space. We'll go to next state, next state, next state, conditioned on action. And then at the end, our final state here that we achieve could be good or bad depending on what we want to achieve. So we might have a goal observation and we want to achieve the embedding of the goal observation. And if we have a sequence of actions, we can evaluate how good we are on achieving this. If we're doing pretty well, that's great. If we're not doing well, we can actually optimize the actions to do better. So if all we look at is this part here, And if we have fixed encoding, fixed dynamics model, we end up with just a standard optimization-based planner that's trying to find optimal actions against the dynamics model and an objective. But actually, we don't have the encoding. We don't have the dynamics model. So what we want is the result of this, if we run it on a good encoding and a good dynamics model, should be a sequence of actions that matches demonstrations. So, and then we end-to-end optimize the whole thing. So we want it to be the case that under the learned encoding, the learned dynamics model, if we run optimization-based planning on it, the result is a sequence of actions that matches demonstrations. If that is true, we have a good encoding, a good dynamics model for planning. You code this all up, this can actually work. There are actually additional benefits. In addition to that, you get a good dynamics model for planning against whatever you might care about at the time. You actually also learn a bit of a metrics, a latent space in which metrics make sense. Because the way it's being planned in here is based on distance in latent space, right? So if you plan against a sparse reward, things are very hard. So we're not just planning against a sparse reward, we're planning against distance in latent space. So that means that we learn a latent space that's very meaningful towards achieving goals. Comparison is with a reactive imitation learner who just sees a lot of demonstrations and imitates them and hopefully does well in the next situation. And also autoaggressive imitation learner, which can look at its recent actions and states, not just on the current observation. Here are some tasks. Navigating a point mass in a maze, having a robot reach for a certain target while there is a cluttery environment, so you need to be careful how you get there. If we look at this 3-link reacher with varying obstacles and goals, universal planning networks, as a function of the number of demonstrations, starts doing better and better and better and learns more quickly than other architectures that we compare with. In principle, if you have a recurrent neural network that's big enough, you should always be able to learn the same thing because that's fully expressive in the limit of infinite data. But what's interesting here is that by having a good inductive bias on the architecture, we're learning a recurrent neural network that has incentives for encoding in a space where planning works. We can learn more quickly. Another interesting thing is that it actually learns something that is like planning. So, it actually plans. So if you have 20,000 demos, and each demo has 40 steps in it, then during training, you're learning to have a representation. If you optimize in it, you end up with a plan that's a good 40-step plan. But it turns out if then you run this thing for longer, over a longer horizon, you do even better. So if you're in a world where planning over a longer horizon is better, you can just extend this rollout and do better. What that means is that really it is learning to plan in some way rather than just a black box that happens to be really good at matching 40-step plans. Another interesting thing is that once you have done this with a few demonstrations, you learn the representation that you can then use to do reinforcement learning. Because you've now learned an embedding into a state space where essentially distance-based optimization is a good thing to do because that's how the planner is set up. And so now when somebody specifies a goal to you, you have a really well-shaped reward because you can embed the goal, embed your current state, and give reward based on how much closer you're getting in the latent space. Question there.
On the previous slide,
Yes?
if it's using an LSTM architecture, like why do the training examples need to be set at 40?
They don't need to be. This is just what we did.
Oh, okay.
And so in this case then, the embedding was learned with a 3-link and a 4-link reacher and allowed a 5-link reacher to very quickly learn through reinforcement learning to solve problems in its own environment. Why? Because the reward is much better shaped in this latent space. Same thing for ant navigation. An ant can learn to navigate quickly, even though at training time when we learn to embed the things that we're looking at here, we actually are embedding a 2-legged version and just a point mass rather than an actual ant. Okay, so those are all about state representation learning. What about the other challenges? Exploration and unsupervised skill discovery. State representation was definitely the biggest one. Exploration, one big thing people like to look at is exploration bonuses. What does that mean? It means that if you do something that is something you have never done before, you get a bonus reward. Even if there's no real reward in the environment. For example, in Montezuma's Revenge, the first time you climb a ladder, you might get a reward for having climbed the ladder, even though there's no actual reward in the game at the top of that ladder. But you get it because you're in a new situation you haven't been in before. And if you do enough of that, then you might be encouraged to, when you see something, to go there because it looks like something else that was new and you got rewarded for in the past. Okay, this is very well understood for tabular reinforcement learning. You just, for every state, you keep track of how often the agent has been there, and then you give a reward maybe 1 over the number of previous times you visited that state. And so once you visit it many times, 1 over the number of times visited becomes small, but if you haven't visited very often, it'll be very large. But if you have a large continuous state space, that doesn't really work. Because in a continuous state space, every state you visit will be new, and then you'll always get the same bonus, that's the maximum bonus. Also, it's not what you want. You actually want to know that if a state is similar to a state you've been in before, you don't want to get as much of a bonus. And so how do we deal with that? Neural density estimation used a pixel CNN to do this. So this is one of the first results that actually made real progress on Montezuma's Revenge. It's now 2 years old. They essentially train a pixel CNN on all the frames you see as you play Montezuma's Revenge, as you go along. And as you train the pixel CNN, when you see a new frame, you can evaluate the probability of that new frame under your density model. If the probability is high, it means it's something you've seen before pretty frequently. You don't give much bonus. But if the probability is very low, you give a high exploration bonus. And so that's one way to essentially get better exploration in this kind of challenging high-dimensional environments. A simpler way of doing something very, very similar is just hashing. So in this paper here, hash exploration, what we did is we took a neural net to to take an observation, embed it, discretize it, put things into a hash table. The hash table is just a discrete set of bins, and we use traditional exploration bonuses for each bin. And so for each bin there, we can keep track how often have we landed into it, and 1 over the number of times you've been into it is your exploration bonus. And also did it on a variety of Atari environments and Joker environments. Here the way we hashed was by training a VAE. So we train a VAE on the observations, and the latent variable in the VAE would be the thing that gets discretized and becomes the hash code. Another thing you could do, variational information maximization exploration, VIME, is we say, oh, well, getting bonuses for seeing things I've never seen before is not really necessarily the best thing. Maybe what you want is you want to get a bonus for when you learn something from an experience. To say, if I am somewhere and from being there, I learned something new, that was useful, and I need to learn to do that in the future again. VIME does exactly that. So it learns a Bayesian neural net dynamics model. So it's a posterior over dynamics models. You have your current posterior. You have your next posterior after your latest experience. You take the KL divergence between the dynamics models. The posterior is over dynamics models. And if that KL divergence is large, it means your posterior probably kind of narrowed and give you more focus on what the world might really be like. You learn something, you get a high bonus. And that also helps a lot in exploration. It helps you focus on essentially parts of the space where you learn new things. Another one, very similar, is curiosity-driven exploration. This one had some of the coolest demos, so this might be the one people have seen most often. It's an important lesson. If you want your work to have maximal exposure, you need to be thinking carefully about the demos that you showcase. It's the same idea. It's about, are you learning something new? But with a little twist, and the little twist is what we saw much earlier in the learning to poke, which is it's going to be in feature space. You learn a model in feature space, rather than in the original space. And to make sure that the feature space doesn't degenerate, you learn also an inverse dynamics model. So you do the same thing that we thought about before, inverse dynamics model, forward dynamics model, both together. And when you have a significant update to your model, it means that you discovered something, and that's great. That means you learned something new. And that actually allowed to learn to play a very wide range of games. And actually what's so interesting about it is that most games are set up that doing new things is actually what you're supposed to do. So you don't ever even need a reward. You can just play against the curiosity reward and still solve a lot of these games, which is kind of cool because that means that there's, in fact, very dense reward. If you think about it, then this way, all these games have dense reward. The dense reward is that you should always be trying to do the things you haven't done before. Mario Bros, this agent would keep running off to the right pretty much forever where there's the new stuff and become really good at that very, very quickly. And also generalize to new levels. There's another type of exploration you might want to do. When you want to do something new, exploration bonuses only reward you after the fact. So you did something new, you got rewarded. It still helps you because your Q function or your policy will internalize that and will encourage you to do something maybe exploratory in the future. But it's not something where you say, oh, I should try this new thing. It's more internalizing after the fact. To explore more quickly, you might want to generate your own goals. You might say, if I want to escape a room, I might want to try windows and doors and set that as your goals rather than waiting till you coincidentally by random motion try the window and notice that something changed there and then say, oh, now in the future I should try windows again. So one approach also tied into unsupervised learning is goal GAN. In goal GAN, the idea is that as you explore an environment, you train a Q function or a policy that is goal conditioned. So you always have a goal and you try to achieve that goal. Then some goals are easier to achieve, some are hard to achieve. The medium, easy, hard, right in the middle are the ones where you learn the most. What goal GAN does, as you set yourself a bunch of goals and try to achieve them, it looks at the ones where you were medium good. It trains a GAN to generate things like that. So generates goals. Goals could be points in space or could be images, could be anything that defines your goal. Tries to generate goals of medium difficulty. Then you try against those and you repeat. Can do it with GANs. Can also do it with images. It happens to be in the image case, it was done with a variational autoencoder, but a very similar idea that you can have a goal condition policy or Q function. You can then train a VAE on things you've seen in the past, sample your latent variable to set a goal, try to achieve it, and repeat. And that way you can have yourself train against many, many, many possible goals. And then if somebody has a real goal in the future, you can take the image that's the real goal, encode it, and your policy will be encoding conditioned to try to achieve it. Yes?
I'm sorry, so in the last slide, how do you assess the difficulty of a goal? What is a medium difficulty?
Yeah, so how do you assess the difficulty of a goal? The way it's assessed is by setting the same goal 3 times. If you succeed 0 times, it's too hard. 3 times is too easy. If you succeed 1 or 2 times, it's considered a medium difficulty goal.
And this is assuming that there's no randomness in there.
No, there can be randomness. There'll be a little bit of noise in how you train your goal GAN, but that's okay. So here is the VAE goal conditioned training in action. So what it's doing here, it's setting its own goals and then trying to achieve them, and then it sets a new goal, tries to achieve it, and so forth. Now, these ways of exploring are pretty good, but there's actually something else people tend to do that we haven't covered yet, which is that you might want to learn skills and be able to reuse those skills. So what would that mean? Let's take a step back. A lot of representation learning is about turning observations into state, because state is the fundamental summary of what you're looking at. And we've seen many, many more than even listed on this slide. And that's important, but how about learning representations of behaviors? Because maybe if we know how to run or we know how to open doors, those are behaviors we can reuse and explore more quickly in the future. So standard exploration proceeds by random actions or perturbations of the parameters, or maybe some exploration bonuses and so forth. But let's look at this environment here. Imagine you're an ant robot, and you get dropped in the world, and you don't get to see where the reward is, but it turns out the reward is always somewhere on the semicircle. But you only find out when you're there. So you're dropped in the world, you run around, and when you step on the reward, you get it, and you get reset, and now the reward might be somewhere else. So if that's the case, what you would want is that after you've been dropped in many, many worlds, you dropped in the next one, that you should say, I should go visit the semicircle and check out where the reward is this time, rather than randomly move around. And so the right behavior to kind of internalize and to reuse would be going to the semicircle. If you're a pushing robot that's supposed to push a block into the target here, and you don't know which block it is, random motion is not going to get you there, or not very quickly. But if you build up a behavior of you always move to a block, then move that block onto the target, see if you get reward. If you don't, next time you move another block, till finally you find the block that gives you a reward, and then you zone in on that one. That's a much better exploratory behavior than random actions. And so the question is, how can we get these behaviors to emerge rather than initial exploration being pretty random? So we want is some kind of compression of behaviors such that we can sample behaviors that are interesting rather than some more naive approach. Here's one way to do this. Let's say you had a lot of tasks that you try to solve. Maybe there's different blocks that need to be pushed to a target. Each task has a discrete encoding. Let's say you're given that encoding. It's just a one hot. You turn it into a latent space variable z, then feed that into your policy, and you have also the current observation, take action. If you've seen enough of those, then maybe in the future, what will be the case is that you're faced with a new task, and you can sample z, and by sampling z, you get some kind of interesting behavior. It might be the wrong interesting behavior, but you'll know, and you'll sample another z, till finally sample the z that gives you the behavior you want, and you're effectively exploring in the space of sampling z's rather than exploring in action space. This, of course, assumes that sampling z has a strong relationships with behaviors you will see, and so you'd want some kind of mutual information, high information content between z that you sample and the resulting trajectory your policy will have from that. This assumes you have a bunch of tasks ahead of time and train against them. It then assumes also that it kind of works afterwards. There's no guarantee here. It's a bit like training on ImageNet, and then after that, fine-tuning on another task and hoping that that's going to work.
This is from state space, right? Not from
the approach can be applied either way. I think these experiments are from state space in this paper, but I don't think it really matters much. That's just, you have to scale up your experiment, run a bigger experiment. I think for this kind of research, it's probably more interesting to work in state space because the experiments will be a lot faster, and the fundamental challenge is in state space. And in behavior space, it's not in observation space. How to force this to happen? What you can do is you can say, we're still going to want it to be the case that there is a z feeding into the policy, and depending on the z we sample, we get different behaviors. But here's what we're going to do. We're going to put our agent in an environment, sample 100 different z's. After we sampled 100 different z's, we'll get 100 different trajectories. We have 100 trajectories, then we do an update, maybe a Q-learning update or a policy gradient update, and we'll get a new policy. We want it to be the case that thanks to the data we collected, after one gradient update, that policy is good. And that's the end-to-end objective we're going to optimize for. It's a meta-reinforcement learning objective. We want it to be the case that if we sample 100 Z's, get the trajectories, and then do an update, the resulting policy will be good. You do that, you actually get really good exploration in all of these environments when you're dropped in them again. So you do a bunch of meta training in these environments where you every time get 100 Z's sampled, you try, and hopefully after one update you succeed. But initially you wouldn't, but after a bunch of meta training, you would be ready. And here's what you get. So when the robot is dropped in the semicircle environment again, when you sample Z, these are the different behaviors you get out, which are very good exploratory behaviors. This is for the wheeled robot. This is for the walking robot. And then this is for the pusher. And you see that all these behaviors are consistently trying to explore the part of the space where it's likely that there is reward that you can then internalize to do well the next time. Learning curve in blue is the approach I described. And the other ones are more standard approaches, either just straight up RL without exploration bonuses or even with exploration bonuses. The tricky thing is even with good exploration bonuses, like let's say something like Vime, you still need to randomly run around the whole space. Everything will be interesting to you. You will not know to narrow it down to the semicircle or to narrow it down to pushing blocks as the interesting behaviors to care about. Okay, so what's left for us is unsupervised skill discovery. So far, as we try to learn these exploratory behaviors, the assumption is that you first get to train in an environment where there are still rewards, and then later, you're fast at learning in a new environment. What if there are never any rewards until later? Can you first have a robot just practice for a long time, learn internal representations of the world of behaviors, and then for the first time be in an environment that has rewards and immediately do well? Maybe. So there's a bunch of work that all roughly does the same thing. And if you look at these objectives, they're almost the same. The experiments they run are not exactly the same. It's a little hard to compare exactly what's going on, but the gist is the same. You still have a goal conditioned policy. So latent variable will be some encoding of your current goal. It could be discrete or it could be continuous. If it's discrete, it will be embedded into a continuous space afterwards. There's the current observation, and the policy is supposed to take an action. And the result will be a trajectory after repeating this a few times. What you can say is, if I want interesting behaviors, what I should have is that if I take a different Z, my trajectory should be different. Because if that's the case, then by indexing into Z space, I can index into trajectory space. And that will give me good exploration. It doesn't get rid of the notion, and we'll see that later, that maybe there's a lot of trajectories and not all of them are equally interesting. You don't know about equally interesting here. All you know about here is that you want your trajectories to be diverse. You want to generate diverse trajectories by indexing into Z space. Or discrete. So the first paper here in 2016, this one looked at discrete space indexing, high mutual information between a discrete variable and a trajectory. Variational intrinsic control looked at a high mutual information between continuous variable Z and the final state of the trajectory. Then diversity is all you need said not the final state, not the full trajectory, is the sum of mutual informations between individual stage at individual times NZ. And then Weyler looked at the trajectory as a whole NZ. It's not really clear what's better or what's worse here. It might depend a bit on the setting. It's kind of a bit of the flavor of research these days. A lot of people think about similar problems around the same time and independently take a slightly different path. And so we have sometimes 4 versions of roughly the same high-level idea here. Cheetah robot is a great one to test on because it has some really funny behaviors. If you look at different Z's that you sample, you get a wide range of different behaviors. This is from the Diversity is All You Need paper. And then this here is on Ant from the Weyler paper. Let's see. And we see Ant is running in different directions for different random seeds, or different Z's that are getting fed into it. And so we see that indeed we can get diverse behavior indexed by the Z variables. Here are the cheetah for, oops, one of them cannot be played. So similar with cheetah, just to kind of show that these different approaches tend to give fairly similar results, at least for now, if you test them in those environments. Where I think the big challenge is, and that's the unsolved challenge, is that if you take a very high dimensional problem, like this guy here, this little robot has many degrees of freedom, which means that there are many, many trajectories. And if you want high mutual information between Z and the trajectory this robot follows, it turns out that it actually never gets up and starts running. It loves to be on the floor. There's so much opportunity on the floor to achieve very high mutual information. It's so much easier to achieve. I mean, our original hope was that, at some point, you're out of mutual information on the floor. You got to do something that involves running, jumping, dancing, something. But with the amount of patience and compute power that we had so far, all it's done is being on the floor. And we even changed the humanoid to be chubby. So we thought maybe a chubby humanoid and smaller humanoid, like babies, like maybe they will decide they need to stand up and start walking, versus a really lanky, tall one might not have an easy time getting up. But even the chubby one just wouldn't start running. It would find more and more essentially breakdancing behaviors on the floor rather than what we were hoping for. And I think that's where this completely unsupervised skill learning gets tricky. If your space is very high dimensional, there's so much out there to try that you need probably a little bit of extra encouragement to get to something that is the behavior that you want rather than just mutual information. Cool. That summarizes what we covered today, and that's it for today. See you next week.